In this video, I would like to derive an expression for the electric potential due to a dipole. So at the end, I'll give you a little context for why this is an interesting and useful thing to do. But for now, let's just do the calculation. All right, so recall that a dipole consists of two electric charges, one that has positive Q and one that has negative Q, and they're a distance d apart. All right, so this is just the general structure of a dipole. And what I'm going to do is calculate the potential at some distance away, so some position in space. And it's going to be a distance r plus from the plus charge and r minus from the negative charge, like this. Another piece of information we're going to need is just what angle this point of interest is at. So I'm going to define that in terms of theta here. So I'm picking angle relative to the line of the dipole. Okay, so first of all, we can just write an expression for the potential. So we have 2 point charges and we can just add them together. So the potential is going to be kq over r plus, that's the potential from the positive charge, minus kq over r minus. So minus because that one is the negative charge, okay, and q is the positive amount. Okay, so one thing that I can do to simplify this is try to get this in terms of just one distance. All right, and I'm going to assume that the point we're interested in is far enough away that r plus and r minus are really close to each other. And in particular, I'm going to assume that if I draw a line here, that this part of the line is going to be r plus long, and then there's this extra bit here. So I'm imagining that that right triangle is also basically an isosceles triangle because the distance of the point we're interested in is pretty far away. And what I can see is that the distance that I have highlighted here is equal to d times cosine theta. All right, so again, I have a right angle here. The hypotenuse of that triangle is d, and this angle is theta, just like the one above, if I assume that r plus and r minus are basically parallel to each other. Okay, so what I'm going to do then is I'm going to take kq over r plus, but then for the second term, I'm going to replace r minus with r plus d cosine theta. So kq over r plus d cosine theta. All right, so this is an approximation assuming that we're interested in a point pretty far away from the charges. This wouldn't work if if r plus and r minus were wildly different from each other. Okay, next I'm going to use just regular fraction rules to combine the two terms. So what I'm going to do is I'm going to find a common denominator, which is going to be r plus times r plus d cosine theta. And in order to make that the common denominator, my first term will be kq times r plus d cosine theta. And then my second term will be minus kq r plus. Okay, so just combine the two fractions. And what I can see is I have these two terms, kqr plus and minus kqr plus. Those are going to cancel. And so when I do that, I'm left with kq d cosine theta over r plus times r plus d cosine theta. Now at this point, I've already used the fact that I'm assuming r plus and r minus are almost the same, that we're interested in a point that's very far from the dipole. So I'm going to call both of these things r plus d cosine theta and just r plus as being approximately equal to r. Okay, so when I do that, I'm going to say kq d cosine theta over r squared, where r is maybe the average distance between the point we're interested in and the dipole. Okay, So this is an expression for the potential due to a dipole. And in and of itself, that may not be that interesting for you. But let's compare it to the potential for a point. So the potential for a point charge is just kq over r. But for a dipole, it's over r squared. And if I take the electric field for a point, I get kq over r squared. And this isn't a proof, but you could calculate the electric field for a dipole. And what you would get is that the electric field for the dipole is going to be proportional to 1 over r cubed. Okay, because you're essentially taking the derivative with respect to the position. Okay, and so what this tells us is that if you have some arrangement of charge and it is if it has a overall net charge, then what's going to be most important is going to be the effect of that overall charge, because it's only going to decrease as 1 over r squared. Even if the distribution of charges has a dipole in it, that one will decrease as 1 over r cubed, and it'll get small really fast. But if you have a distribution of charges where the net charge is 0, then the 1 over r squared part is just 0. And so then the dipole part is going to be most important. All right, so there's actually this whole hierarchy of different arrangements of charges that we can consider. And there's a name for it. So if you go on to take a more advanced E&M course, this is a really important tool that you make use of all the time. So essentially you can take any arrangement of charges and split it into a monopole part, a dipole, a quadrupole, and it actually just keeps going. There's an infinite number of these. There's, for instance, an octupole. And it keeps going, like I said. All right, so the electric field for these, well, for a monopole, which is just the charge. So we know what the electric field for a point charge is. That's going to go like 1 over r squared. And for a dipole, we just discussed, it's going to go like 1 over r cubed. And then following the pattern, a quadrupole will go like 1 over r to the 4th. And an octupole will go like 1 over r to the 5th. So ordinarily, the way that you would treat these is you would calculate the monopole term. If it's not 0, then you're done. If it is 0, then you calculate the dipole term. If the dipole term is 0, then you have to calculate the quadrupole, and so on. So only the first one of these that is not 0 is going to end up being important, because we're very often interested in distances that are large compared to the actual structure that we're interested in, if it was, say, a molecule. All right, and then how to make sense of these? Well, we know what a charge looks like. That's just, say, a positive charge. And we know what a dipole looks like. That's a positive charge and a negative charge that are separated by some distance. Well, if the dipole for a charge distribution is 0, then the next possible arrangement is a quadrupole. So what that looks like is we have a dipole, but then another dipole oriented oppositely. Okay, so you can imagine kind of a square of charges. So this has no dipole moment, but it will have an electrical interaction, and so you can calculate what the most important part of that interaction will be by calculating the quadrupole moment. Okay, what about an octupole? Well, again, we can have two quadrupoles that cancel out. So what this will look like is, let's say, something like this. But now we want to have one cancel it, so let's say that we have a minus, and a plus, and a minus, like this, and then back here, there's going to be another plus. Okay, so this cube, for instance, of charges, again, for that charge, it's neutral, there's no dipole moment, and now there's no quadrupole moment either, so that could be a way to represent an octupole. And you could just keep going. So like I said, you can have higher and higher moments, these are called, for some arrangement of charges, and only the first non-zero one typically matters as you get far away.